This is our next to last colloquium. Actually, it's something we're trying for the first time. Hopefully, it won't be the last. So this is sort of like an informal thesis event. So these are talks by our amazing grad students that are going to tell you a little bit about the research they've been doing. And first off is Joey Contreras. It's been my honor to work with him for the past like 2 years. And we figured out quantum gravity. It's done. It's finished. For Joey's going to explain to you, right? Really? No. It's a joke. It's a joke. So Joey's going to tell you about modified commutators versus modified operators in quantum gravity minimal length scale. So Joey, take it away.
Okay. Hi everybody. My name is Joey Contreras. I am a grad student here at Fresno State, and I am currently wrapping up my master's degree here. I'll be graduating this semester, and for the last 2 years I've been doing research with Dr. Singleton over here, Dr. Bishop back there, and then also our new grad student Pete. And yeah, today I'm going to be talking about essentially that work, some current ongoing work, and little things from my thesis. So without further ado, let's get started. Okay, so before I get started, I want to talk about the outline of what I'm going to go over. First things first is I'm going to talk about a motivation for minimal length, kind of like why do we care in the first place, why do we think there might be a minimal length, and also why is it a question worth exploring. After that, I'm going to talk about the consequences of a minimal length. And so if it is a thing, what type of physical consequences might we see, and also what kind of interactions might we be able to predict according to theory. After that, I'm going to talk about minimal length in our model in 1 plus 1D, just because it's a simpler case and it's a little bit easier to break down. Once I go through the nitty-gritty of that, I'll talk about extending this to 3 plus 1D and some of the interesting results we found in our current ongoing work, followed by summary conclusions, and then we can call it a day. So, why quantum gravity? Classical mechanics and quantum mechanics provide great approximations, but sometimes they fall short. And when I say great approximations, like, I really, really mean it. I mean, think about it. They've gotten us to the moon, we've detected gravitational waves, we have self-driving cars, Lord of the Rings extended cut. I mean, the gifts never stop coming. But nonetheless, there are situations where we kind of need a bit more. Black holes are an excellent example of a situation where this happens, because while general relativity can for the most part handle black holes to a certain extent, as you probe closer and closer to the event horizon, quantum effects start to become relevant. And at this point, once again, you need a bit of a new theory. There have been many approaches to quantum gravity so far. Quantum field theory, very popular one. Double special relativity, a not so well-known one, but nonetheless there. I'm sure you've all heard of string theory in some form or another. And then finally, the focus of this talk, the general uncertainty relation. So, a central question of quantum gravity, and one that we're interested in very much, is whether or not space-time is continuous or discrete. At low energies, space-time does appear smooth. There doesn't appear to be any fundamental building block or ridge. However, there are theoretical arguments for discretized space-time at high energies. This is sometimes referred to as ultraviolet cutoff. And it's this idea where at very high energies required to probe small distances, those energies will in turn affect the curvature of space-time. And so effects like these are thought to occur at the Planck scale, which you get just by arranging these constants to get the units right, or the Planck energy, which, similar vein. Now, when I talk about minimal length, I want to be clear here. I'm not talking about a literal minimal length, but rather a minimal length of observation. Essentially a lower bound on the uncertainty in position, and more on this in a second. Now, if such a minimal length exists, what might be a consequence of that? Okay, photon dispersion, a potential consequence. So, theoretically, photons of different energies should have different velocities due to interactions with the fabric of space-time. We're, again, assuming a minimal length is a thing here when we're talking about this. Emiliano Camiglia proposed a modified energy-momentum relation for photons. Now, we see here for the most part, it's the exact same relation, right? Like p squared c squared equals e squared. And then there's a mass term, but again, because this is for photons, that mass term goes away. And so it almost appears like the standard relationship, except we have this extra function right here, or corrective factor, which depends on the ratio between energy and the energy of quantum gravity. Now, the quantum gravity energy is generally set to be the Planck scale, so 10 to the 19 GeV. This is just something done by convention, and I can't really give you a solid, fundamental, amazing reason why that is the case. But nonetheless, it's worth exploring. So, implications of modified energy momentum. Taylor expanding the modified energy momentum from the last slide and ignoring the higher order terms gives us this expression right here. And I wanted to say a few things about this before I go on. Note that we have this parameter right here. This is just a parameter associated with your theory of quantum gravity. It can be positive, negative, big, small, who knows. Once again, we have the ratio of the energies that pop up here. If you follow through with this, you end up with this dispersion relation. And so we see here what I was talking about when I say photons with different energies could then be predicted to have different velocities. We have C, which is what it should be, and then once again our corrective factor, which depends on our parameter as well as the ratio of the energies. Now, what is a potential way to check for this, right? Well, one potential way is to measure for time delay in photon emissions from distant sources. And so, gamma ray bursts. These are excellent candidates for this because, well, for one, they're highly energetic photon emissions, and they come in two classes or two categories, short and long gamma ray bursts. They're categorized by their burst interval, which is just the amount of time that the emission takes place. It turns out that short gamma ray bursts are preferred for testing because there's less intrinsic lag in these measurements. Generally, sometime under 2 seconds. I don't know if 2 seconds is like the verbatim cutoff, but from 0 to 2 is generally that range when you're talking about short gamma ray bursts. And so, we see that different energies might lead to different arrival times, and we have this expression right here that kind of shows us that relation. If you look at this right here, we have different times or a range of times, for example. Once again, the parameter pops up and this little ratio. Up here would just be the range of energies associated with the photons. And L is just the distance that they travel as they go through the curvature of space, or just flat space even. Okay, GRB 090510. This is an interesting one. So this was a gamma ray burst detected by the Fermi telescope. Here's the energy range that they had for their detection. So from 35 MeV to 31 GeV, very large energy range, and this is where the delta E comes into effect. The burst interval associated with short gamma ray bursts is also here, and once again, it's going to fall in that time range that I was speaking about, where it's somewhere between 0 and 2. So we have this term, we have this term, and using this, scientists were able to estimate this ratio right here, or the absolute value of it. Using this estimate, and also, well, measure, really. Using this measure and an estimate of the distance traveled by the emissions, they were able to kind of calculate what the energy of quantum gravity should be. Now, I should note here that the expected result was that we would see quantum gravitational effects well before the Planck energy. However, it was found from the calculations here that the quantum gravity energy would be 1.6 times the Planck energy. Now, this is a bit of a problem. I mean, it's a 1 times the Planck energy would have been better. But yeah, a 1.6 is a little concerning. And honestly, if you think that's bad, for other data, it was as high as 102 times the Planck energy. And so whether or not that's a damper on minimal length, well, that remains to be seen. So, observation currently shows no such photon dispersion. And so does this imply that space-time is smooth and that there is no minimal length scale? Well, what about another approach to minimal length, if you would humor me for a moment? Okay, another approach. Minimal length can be approached, as I said earlier, via uncertainty relations. This method was popularized by Kempfman and Manganu, and essentially what this boils down to is modification of the position momentum commutator can lead to a lower bound on position uncertainty, and I'll go deeper into that in a moment. To better understand this, we need to explore modification of the Heisenberg uncertainty principle. So, minimal length can be thought of as a minimal uncertainty in position, right? From quantum mechanics, Heisenberg gives us this relation. Delta x, delta p greater than or equal to h bar over 2. Using this relationship, we can find a proportionality for the uncertainty in position that depends on the inverse of the uncertainty in momentum. So, the Heisenberg Uncertainty principle gives us this expression and this proportionality. Now, the thing about this is, because there's no bound on the uncertainty in momenta, it can get as large as it wants, and because of that, the uncertainty in position would just go down, 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 and eventually hit effectively 0. And so we see there's no minimal length scale from the Heisenberg uncertainty principle, at least not on its own. You'll humor a little detour for a moment. Consider this theoretical argument. Now, to probe small uncertainty in position, we need very large momentum. Very large momenta can be associated with very large energy, and because of the Einstein relationship, can be associated with very high mass. And so, at a high enough momentum, a black hole will form, or micro black hole. Now, for a black hole, the uncertainty in position is proportional to the Schwarzschild radius, which is also proportional to the product of the gravitational constant and the mass associated. So, to just backtrack a little bit, we go from mass to energy to momentum. And so this relationship up here implies that the uncertainty in position is proportional to g times the uncertainty in momentum. So, combining the Heisenberg uncertainty relation and the previous slide results in the following proportionality relationship for uncertainty in position. In fact, if you look at this graph right here, we can see where the individual things are. This blue line represents the standard Heisenberg uncertainty relation. This green line is where the proportionality to g and the mass came into effect. And this red curve is the resultant of them all. And so, looking at a curve like this, we actually do get a non-zero minimum value for the uncertainty in position. And also very interestingly about this is that within the context of black holes, this actually makes really good sense. Because the uncertainty goes down as the black hole accretes more and more mass, or gains more and more mass. And at some point, further mass would just increase the size of the black hole, and thus increasing the Schwarzschild radius, so this uncertainty in position will continue to grow. Now, there's another way of getting that curve. This is called the generalized uncertainty principle. So Kempman and Mangano proposed the following relationship, where they modified the position in order to give this new relation right here. Now, this relation is nice because, well, we have this parameter beta, which again depends on our model, but it leads to a proportionality for the position uncertainty that looks like this. Seem familiar? So, we have another way of getting this curve, a more general way, and it all follows from this idea of modifying operators or modifying commutation relation. So just to point out, yeah, the minimal length will be at this local minimum right here. So, relationship between the commutator and the Heisenberg uncertainty principle. The uncertainty principle depends on the commutation relation via this expression right here. And so making changes to the commutator can give us different uncertainty principles. This being IH bar just eventually boils down to here. And so the above generalized uncertainty principle, or the one that was on this slide right here, can come with the following modified commutator, where we have the standard expression IH bar and then a corrective factor, which does depend on this parameter. It keeps popping up over and over again. And so at this point, it's a very interesting question of whether or not it's the operators or the commutators that will define a minimal length or determine a minimal length. So, consider this example. If we have the same generalized uncertainty principle from before, with a modified momenta as well. So here we have the exact same expression, only now instead of just x being primed, p is primed. So we have this following proportionality relation for the uncertainty in position, but notice here that the details or the specific behavior of the modified momenta will actually determine whether or not a bound happens from this, or a minimal length uncertainty. And so it would appear safe to say that modification of the operators is actually crucial to determining a minimal length, and not so much the commutator, although it is related. But yeah, operators went out. And so here's where our model for 1 plus 1d comes into play. We modified the position and the momentum operators in order to maintain the standard form of the commutator. This was neat because it led us to the standard form of the Heisenberg uncertainty relation. And we found two sets of position/momentum operators that satisfy the above expression. We have this set right here with Cauchy-Tanch, and and then this set right here with arctan. Now, I want to say some things about these sets that we have. Notice at low p, they actually simplify to the standard expressions. At low p for here, cosh just goes to 1, and we have I h bar partial p. At low p over here, tanh just goes to its argument, and so this pm, or this max momenta, cancels out, and we're just left with p. So this simplifies. Similarly, we have the same thing here, where at low p, this ratio is effectively 0. It goes away. We get the same thing. And once again, arctan just goes to its argument, and so everything cancels out except for the standard p. And so, very convenient thing. And it really comes from this idea of bound momentum operators. In fact, we started with the bound momentum operators and then modified the position such that the relationship would be maintained. Now, this is loosely motivated by Born-Infeld electrodynamics, where there's such a thing as a bound electric field. So here, we have the operators that's simplified in the way I said at low p, and they also have bounds of plus or minus pm at very, very high p. So this graphical nature of these functions was actually a very, very important thing as far as why we chose them to be our operators. Please forgive the typo of p naught here instead of p max. That's my bad. Don't at me. So, moving on. Okay, recovering a minimal length. So, when the momentum reaches its maximum value, we do find a minimum value for the uncertainty in position, according to this relationship here. And graphically, this is how it looks. So, we get an uncertainty relation, that's great. We don't get the cute little curve that the black hole thing had, unfortunately, but that's okay because this model does some other things for us, even though it might fall short, so to speak, in others. And one of those things is that this model will actually address photon dispersion. And so let's go ahead and get into that. Okay, so modifications allow for the standard form of the energy-momentum relation to be retained. So that would be this expression right here. For photons, the energy expression simplified very much. Once again, this term drops out. And we just have these expressions right here, where if we write them in the prime form, we see the standard thing just pops up over and over. Now, going to the dispersion relationship from earlier, we find that there is no corrective term for the speeds of the photons, right? So all the photons should arrive at the same time. And this is nice because there's no conflict with observational data from the gamma ray bursts. In fact, this feature right here that we see, where photon dispersion is kind of avoided, was another reasoning for the selection of the operators that we chose. So, it's all coming together. Let's see. Extending the model to 3 plus 1D. To account for multiple directions, we modified our operators as follows. So you see in these sets, they're essentially the same thing, except they're now the vector properties that we need associated with multiple directions. Another neat thing about these operators is that they're in fact rotationally invariant, which is always a good thing. It makes life easier. However, it is no longer possible to maintain the standard commutator in all directions. In other words, this relationship kind of runs us into some very interesting things, so to speak. So, for hyperbolic tangent, if you'll consider this simplified version of a vector where it just travels in one direction, the commutator we found ends up being this large expression. Now, when the indices are different, all the standard relations are obeyed, it just zeroes out. When they're both equal and both equal to 1, we actually do recover the standard commutation relation, provided it's in the direction of motion. For the orthogonal directions, when both of them are equal in either 2 or 3, we get this funky looking thing. And to be honest, we're not quite sure how to interpret it yet. Once again, this is ongoing work, and it is something that we are trying to tackle at the moment. And there is another paper in the works regarding this sort of thing. But nonetheless, it's an interesting result that I think is worth bringing out. For the inverse tangent commutator, pretty much the same ballgame. We look up, we have the simplified version of this vector, and we have this large commutation relation right here. Once again, if you let the indices be different, everything zeroes out, it's all fine and dandy. If you let them both equal 1, where that's just the direction of motion, you get the standard thing, and in the orthogonal directions, we get this funkier looking expression right here. So, moving on to rotation generators. we can actually use these modified operators to find the generators of rotation and of boosts. The angular momentum operators in particular can be found with the following expression. However, it turns out that these don't satisfy the standard algebra, where it's just this relation right here, due to some common factors shared through all of them that we found in the map. Now, we, because we're such a big fan of redefining operators, just divide through by this factor, and now these operators will actually satisfy this algebra, which is fantastic because, well, it avoids Lorentz invariance violation and things like that. The boost operators behave in a very similar fashion. The boost generators can be expressed like this, and so before we use this expression, we had to define time and energy operators to go into it. And so we just defined them as follows. Forgive the funky notation, we just didn't want to use a bunch of different E's, and so do what you will with that. Now, going through, we find that once again, they don't entirely satisfy the algebra, but it's by a common factor, which we just divide through by, and suddenly these right here will go through and satisfy all the standard algebras. And so that's really the big thing here, is that the standard algebras can be obeyed by these choice of operators. Photon dispersion can be avoided, and so on. Yeah, there's just lots of benefits to them. So to summarize, while spacetime is smooth, there may be a minimal length of observation. And this may pop up in theory mostly, but if it pops up in theory and it pops up in the observation itself, I mean, is it really an abstract thing? Who knows? For the uncertainty relation in particular, it is the operators and not the commutator that determines the minimal length. And just to like reiterate or rephrase what I mean by that, you can have a commutator relation that gives you a minimal length, but if you modify the operators in such a way, that same commutation relation or that same commutator might not give you the bound or the lower bound that you're looking for. It is the operators that determines this. Bound momentum operators can account for photon dispersion while still providing a minimal length scale. Because this is new territory and there's just so many different approaches to this, it's going to happen that sometimes things are going to clash with one another. But when you can have a model like this that doesn't kind of like butt heads with any other predictions or fall short in some kind of way, I think it only helps and gets things forward. The 3+1 versions of these operators will obey the standard commutation relation, provided it's in the direction of travel. Once again, we're working through the orthogonal direction. We'll see where that goes. It's definitely an interesting thing nonetheless. And then finally, the rotation and the boost operators can be calculated from all these modifications. And if we redefine them properly, we can still obey the standard algebras, which only makes life easy. So, thank you all so much. It's been a hoot, it's been a blast. Yeah.
Thanks for a great talk. And by the way, did you guys get all the references, like the Heisenberg and stuff like that? Anyway, so.
Yeah.
Anyway, so let's take a few questions now, and then our next speaker, Patrick. So let's have a few questions now if you guys have questions, and then at the end we might have questions overall. Tori?
So when you do this consideration, do you have in mind like a privileged observer? Because I think if you do like Lorentz transformation or you change chart in the system, I expect that the minimal length will change. So do you have in mind like a symmetry breaking that would like bring up a privileged observer where you do find a minimal length?
I'm not sure, and feel free to jump in if you want. The multiple observer thing we haven't really delved into very much, right? I mean,
No. So I mean, the point is that we're trying to have the minimal, have our cake and eat it too. So we have a minimal length in this. Most minimal length theories actually do have Lorentz invariance violation, and so you have to confront that. Now, people haven't seen evidence of that, so they've looked in like these gamma ray bursts and everything like that, haven't seen a sign of it. So strong theoretical arguments say there should be a minimal length, but we don't see any evidence of it. So this is our attempt to kind of have a minimal length, but avoid the nasty Lorentz invariance violation that we haven't seen.
okay.
That way that nobody's seen. So, more questions? Okay, let's thank Joy again. Patrick has been with us
Too long.
we wish you could stay longer. Yeah. So he's because he came in did part of the undergrad curriculum again, did some research with Dr. Ho, and basically is finishing up his master's degree research with our newest faculty member, Tori Vitale. So Patrick has done amazing work. He has like 3 or 4 published papers, several conference talks. And Tori, do you want to say anything about Patrick?
Well, apart from the fact that I will miss him because he has been a great collaborator since 2018. He even reached out to me before I came here. So it has been a spectacular period, so thank you, that's for sure. And I hope you will continue the good work.
Yes. Well, he will. So actually, Patrick actually was accepted in many PhD programs, and actually is going to go to University of Maryland, right? And continue in research sort of in this vein, yeah?
Chemical physics.
Chemical physics, okay. And so actually, I should say, I forgot to mention this, Joey is actually going to UC Merced next year and working on astrophysics or something like that, right? Okay. Anyway, so Patrick is going to tell us about exploring the quantum many-body problem with cold atomic gases. So Patrick, take it away.
Okay. Hi, so I'm Patrick Kelly. Yeah, you heard all that. So I'm going to be talking about theoretical and numerical methods for studying cold atomic gases. There's Democritus looking very miserable in a cemetery, I think. Yeah, nothing exists except atoms and empty space. Everything else is opinion. 400 BC. So yeah, I'm going to talk about cold atomic gases, what they are. I'm going to talk about the Fermi-Hubbard model, which is the most common model used to study these systems. I'll talk about a theoretical method that's widely used called Bcs Theory, and with GRPA, which is another add-on to it. I'm going to talk about probes in quantum systems and how we actually study them in the lab. And I'll talk a little bit about theory of correlation functions, more stuff about correlation functions, and then I'll talk about the sort of observable we're most interested in, called the dynamical structure factor. And then I will give our earlier results and then our more recent results for the dynamical structure factor. And then I'll finish it off by talking about maybe how future students could take this research further. So, what's the motivation for studying cold atomic gases? You can't study the insides of complex systems like superconducting materials, or at least the ones that aren't understood with BCS theory, and other quantum many-body systems like the superfluid interior of a neutron star. And there's also exotic phases of matter that show up in quantum statistical mechanics, like superfluids, that are difficult to study. So one way of doing this is to use a cold atomic gas as a sort of simplified model of a more complex physical system that would be easier to create and then probe in a laboratory setting. So what experimentalists do is they'll take, for fermions, they'll take lithium and potassium atoms, they'll cool them down to the microkelvin to nanokelvin range, very low temperatures, and then they will use lasers to embed them in what's called an optical lattice. And here's sort of the picture here. So you get this checkerboard pattern of minima in this potential, and the atoms will hop around between these minima points, and they'll spend most of their time at the minima, and they'll very quickly transition between them. Under certain regimes, when the number of particles n equals the number of lattice sites, and when the number of spin-up particles equals the number of spin-down particles, you can get one of these exotic phases of matter I was hinting at. It's called supersolid. It's a superfluid with a checkerboard density modulation. So it's a weird sort of thing that's not really a fluid, not really a solid, sort of has properties of both. So here's the model, the Hubbard model. It's a Hamiltonian that is commonly used to study cold atomic gases. We have a kinetic energy term here and a potential energy term here. And like I said, we're using quantum Monte Carlo and BCS theory with GRPA to study this model, try and basically solve this solve the Schrodinger equation, or at least observables that you study with the Schrodinger equation for this Hamiltonian. And it looks relatively simple, but there are no analytical solutions. It's actually, there's a huge amount of complexity hidden in here that sort of emerges from it. So the kinetic energy term models the hopping around of particles freely on the lattice. The potential energy term basically allows for two particles with opposite spins to meet up at one lattice site and bind and form a pair. But when they're not on the same lattice site, when they're even just separated by one lattice site or one lattice spacing, they don't feel each other. So it's a very simple model still, like I said. They only interact when they're on the same lattice site. You could imagine more complex Hamiltonians where you have extended interaction, but that's not what we're studying. This is like the most simple thing you can imagine that still has interaction. And because of Pauli exclusion, if two particles with the same spin meet up, they can't meet up because they can't both be in the same state at the same time. So that's what I'm trying to visualize here. So first pass of sort of approximation, mean field-based method is Bcs theory. And this is the Bcs Hamiltonian. You can derive this from the other Hamiltonian I gave. The true Hamiltonian is what we usually call it. Just these symbols here, mu Bcs is a chemical potential. Basically tells you what all chemical potentials tell you, that it's the cost, energy cost of adding or subtracting a particle for your system. You have the pairing gap, which is a little harder to interpret. The dispersion relation, which is the energy there of energy as a function of the momentum of the particles. And then these are the creation and annihilation operators that are used in second quantization. They basically, they're what the little devices, mathematical devices that actually control a particle moving from one state to another, or one lattice site to another. So how do you get it from the true Hamiltonian? First you transform the momentum space from position space. Then you assume only particles with, basically the particles have equal and opposite momentum, the pairs, and that the system is made up of a fluid of just pairs with these equal and opposite momentums. And then you replace this term here that has four creation and annihilation operators. You use mean field arguments to turn it into one where you only have two. So it's linear in these pairs of operators. Then you switch to the what's called the Bogoliubov quasi-particle basis, which is you basically say, I have my real particles I'm dealing with. I don't want to deal with those anymore. I want to think about new kinds of particles, but they're quasi-particles. They're excitations in the system. But in quantum mechanics, it seems to be the case that it's just very natural. You can always dream up new particles. Like you can talk about, oh, if I've got vortices in my system, those are going to be my particles. Or if I've got sound waves, well, no, those are going to be my particles. And you have rotons or phonons. And in this case, you have Bogoliubons is what they're called. So it's a nice name after whoever he was, some Russian guy. Yeah, so you define new creation and annihilation operators for basically creating and destroying or moving around your Bogoliubons in the momentum space. And interestingly, the whole point of all this is you and you get a Hamiltonian, which, look at this, get rid of this term, just look at this one. Now compare with this guy. That's a non-interacting Hamiltonian. That's like a Hamiltonian for an ideal quantum gas. And so now you've done all this and you've done all these approximations and done some math, and you've got something that looks like a non-interacting system, which is obviously going to be easier to solve than one that has interactions. And that's the main advantage or reason we do all this stuff. And you get a new dispersion relation that's related to the old one and your original parameters in your system. So that's BCS theory, basically, for at least for cold atomic gases. Then take a step further, and you apply linear response theory, which I talked about last semester, and I'm not going to bore you with, but it is very interesting, worth learning if you ever have the time, because it's sort of the foundation for. It's like this untalked about thing that actually a lot of important stuff comes from, and you only really, it seems magical until then you read about linear response theory and you understand, okay, this is where all these things like this come from. This is a response function. It basically, it's the BCS level approximation to the response functions in linear response theory, and the gist of it is it tells you how your system responds to a general perturbation, and I will talk a little bit more about that. Then you can use the fluctuation dissipation theorem. It's a really important idea in statistical mechanics. And you can show that this guy is proportional to what we want, which is the dynamical structure factor, which is directly accessible in experiments. It's proportional to the dynamic doubly, the double differential cross-section, which is what they actually measure in scattering experiments. And then you can do GRPA, which I'm not going to talk about too much, but it's basically an extension of BCS theory, and you can get even better results for these guys from it. You basically form linear combinations of all your observables and then use those as a new perturbation. But this is the most important stuff. So I will talk a little bit about what does SQ omega actually mean, SNN Q omega. So imagine, and this is more generally about just quantum mechanics in general, but imagine you're in a dark room with some mysterious object, and you want to figure out what it is, you want to figure out its properties, how it's moving, yada yada. And how do you do that? In quantum mechanics, we sort of have this problem because we don't really have access to the exact, with infinite precision, dynamical variables of the system, like the position, the momentum, like you guys were talking about, Jimmy was talking about. You have uncertainty relations. So Schrodinger only gives us probabilities, not trajectories. So we need to rely on expectations and correlations to study the system. And this is sort of the idealized picture of how you probe a quantum system. You've got some probe that emits a beam. Here's your sample. Stuff scatters off of it. Maybe it's a beam of neutrons, and then you sort of collect and see what's coming out of it. What's more of this, less of that. That's basically the idea. More of momentum of neutrons with some momentum, less of neutrons with some other momentum. And my analogy was, in the dark room, you just poke it with a stick and whack it and see if it maybe gives off a noise or something like that, or it's gooey and it sticks in the stick, or whatever. You can also use light. I guess it would be easier to turn on a flashlight. But, so we're, in quantum mechanics, we're sort of stuck using expectations, and the sort of generalization of an expectation or an average is a correlation, or a correlation function. So how do we express this sort of dependence on how a system responds to some probe? So what is a correlation function? Like, what motivates its definition? That's the definition. The why. First time I saw this, I was like, okay, that's great, but why? Well, think about the probability, the joint probability of some event happening. Say the probability of both, I don't know. This could be the position of two particles. This could be the probability that you find particle near X and then the other particle near Y. Well, break it up into a part that is independent, where they're not the positions aren't influencing each other or their likelihood, and a part that can't be broken up. Then you plug that into just the definition of an average, where you multiply by x and y and then take an integral over all space. You get this, define this as your correlation, and then rearrange, and then you've got that. And it's basically related to the part of the joint probability that contains the dependence of x on y and vice versa. The sort of irreducible part of the randomness that isn't just the randomness that's or the contribution to this product that comes from x depending on y and y depending on x. And if you have an autocorrelation, that's just the same quantity at different times. So I have a at 0 and a at time t. Say. Here's an example from a classical system. This is from a molecular dynamics simulation I did. And it's called the velocity autocorrelation function. It basically tells you how the velocity of a typical particle in a fluid at some time depends on what its velocity was at a later time. So the particle's moving around and it has some velocity, say this moment you start your clock running, and then you say, okay, well what is velocity likely to be sometime later? And you can, with this guy, you can get a sense for how long it takes for the system to sort of forget what its velocity was originally. So it starts out at some maximum, and then it goes down. That's basically reflective of, and the reason these are interesting and why we're interested in them is because they tell you about hidden processes that are going on inside a complex system like this. This is just a classical many-body system. So this goes down because the particle is experiencing collisions and drag from its neighbors, and then goes up again because the particle sort of drags other particles along with it, creates a little vortex, and then that vortex whirls the particle around and starts it going in the opposite direction that it started in. And at any given moment in the fluid, there are all these little transient temporary vortices going on. And then eventually, over long time scales, basically the particle forgets about what its original velocity was, and the two gradually decorrelate. And that's what I was trying to show with this sort of bouncing around the random path as the particle wanders off into the rest of the fluid. 50 minutes. So here's some interesting correlation functions that allow us to sort of carefully derive the dynamical structure factor. We start out with this thing called the Van Hove function. It's nice because it's defined in sort of quantities that are a little more intuitive, position and time. But that's its definition. Its sort of intuitive interpretation is it's the number of particles at point r and time t, given that there was a particle at the origin of your coordinate system, so at point 0, at the time your experiment started, so at time 0. I don't know if that was useful or not, but that's what a book I read, that's the definition or the intuitive meaning they gave for it. Yeah, these are just density operators for the number of particles per unit of volume at r and at 0. Do a Fourier transform, get this thing, intermediate scattering function. It's a function of momentum and time, so it's maybe a little bit harder to interpret, but it's still useful. Then you can basically switch to an imaginary time, and I call that tau. And this guy's important, this imaginary time intermediate scattering function, is because it's what QMC, quantum Monte Carlo, gives, which is a method that's a very powerful method. It's used everywhere. And it gives it, at least for the system we're studying, the super solid, it gives the results exactly. So you can basically, you want to get, what I mean when I say exact is, you run your simulation for, I don't know, however many times, you average your results, it's off by some amount from the true value, okay, we'll just run it more. It'll get even closer to the true value. And if you run it an infinite number of times, the prediction from Monte Carlo will come arbitrarily close to the true value, at least for the system that we're studying. In general, quantum Monte Carlo will not do that, but it's still a very powerful method that can give you very highly accurate results that are close to the true values. So we can also get it very quickly and easily from our approximate GRPA results. So it's sort of the natural quantity that we would want to use if we wanted to, say, compare the accuracy of GRPA to using the QMC data as sort of an objective standard. So, yeah, exact results from QMC, approximate results from GRPA. And that's sort of what my thesis was about, is assessing how good GRPA really is, at least with this sort of system. So you take one more temporal Fourier transform, go to omega space, and then you've got the dynamical structure factor. This is its, I mean, it's its definition, but you can derive it from other defined quantities. And its sort of intuitive meaning is it's the probability of the system absorbing k units of momentum and omega units of energy from the probe, where k is the change in momentum or change in wave vector of the probe, and omega is the change in frequency of the probe as it comes in, and then leaves the system. Is proportional to those response functions I was talking about from linear response theory through fluctuation dissipation. At least I should say it's proportional at 0 Kelvin. It's a little more complicated at finite temperature, but it's still a relatively simple relation. There's an exponential in there. And here are results from 2020, a paper republished in 2020. This is the GRPA or BCS plus GRPA level results. Here is the quantum Monte Carlo results. You'll notice that this is very smooth, whereas this is like striped. And that's because, unfortunately, QMC is so computationally expensive that we can't, we don't have the budget to be able to do this at higher resolution. And no one does, because no one has yet figured out how to simulate a system large enough to where you can get this sort of resolution and actually do that sort of Monte Carlo computation, which is unfortunate, but maybe in a couple decades you will be able to do this. And it's also unfortunate because, in some sense, I mean, Monte Carlo tries to, what Monte Carlo does, and I didn't say this in the presentation explicitly, is that it's not solving this approximate Hamiltonian, this guy. Monte Carlo is solving this guy. So the true physics, it's Monte Carlo, the real reason it's so interesting is because it solves the true model. So everything that you could possibly know in that model or in that system, you know, it's in there somewhere, but unfortunately the resolution's so low that it's like we're looking through a fence. There's a beautiful garden, but this fence is in the way, and we're blocked. We can't see some parts, so our vision's a little bit crummy. And this is, we're looking at a picture of the garden. And not a very good one, maybe. Actually, no, this is a very good picture. This is still like, it still works pretty well. Like, we get this nice, and you can see, I mean, you don't need really a quantitative assessment. You can see this seems to work pretty well. And this tells us interesting things about the system we're studying. Because remember, we're studying something that looks like this. But that's just a picture, whereas this tells us something about the real system. And what this minima, I will draw your attention to here at pi, that's telling us, and notice that this is on the 0, so here's omega, omega is 0 along this line. This is telling us that if you send in a wave into your system with this wave vector, I said k and the, yeah, but qk, it's the same thing. with wave vector pi pi and energy 0, well, actually I should say, not sending a wave, that it costs 0 energy to impose a wave vector with this value on the system, which tells you the system is already basically arranged in a way where it can accept that wave vector. And that's how we know that there's this periodic density modulation in the system. It's already arranged in this wavy pattern, just naturally. But that's how it likes to be. And that's sort of how, the spirit of how we sort of figure out what's going on inside a quantum many-body system when we really can't actually look at it, right? So there's a lot of stuff going on here, but it's basically the same information as this. These are just this, and this, and this. These are just vertical slices of this, basically. So, actually, I take that back. These sub-panels are the vertical slices of this. These main panels are the intermediate scattering functions I was talking about, these sort of things that we can get exactly. And I should also say that another problem with Monte Carlo is that to get the dynamical structure factors, you have to do an inverse Laplace transform. That severely affects the accuracy as well, which is, again, why these guys, these intermediate scattering functions, they're the sort of natural quantities for objective comparison between GRPA and QMC. Now, we had the idea, it was a good idea, but it didn't work, but you see this discrepancy? Well, let's see, where did I say orange? GRPA is orange. You can see it, it's biggest in this one. So that's our approximate theoretical method. Blue is the QMC, that's our exact method. See this discrepancy? We thought, okay, well, what if we go back, well, it's not there explicitly, that's annoying. See this U? There will appear in this guy somewhere in, I don't know if I forgot to write it or if I'm forgetting where it shows up in here. But, what?
It's in delta.
It's in delta? Okay, I couldn't remember that. So we thought, okay, let's fiddle around with the potential energy, the U parameter that we use in Bcs Theory and GRPA, and sort of find which value of U will minimize the difference between this guy and this guy through a sort of effective potential idea. So I used a chi-square plot. I ran a bunch of GRPA calculations, each for a different U effective to get these nice smooth curves. And I found the minima, found that minimizes discrepancy between the two data sets. And then I plugged that UF effective back into the GRPA code and tried to see if we could get results that were closer to QMC. And it works in the sense that it's closer, at least for the intermediate scattering functions. Dr. L?
This system in the real world, what do you use as a model to do this? You are doing a super fluid or you are doing super solid?
Well, a super solid is a super fluid, but it's got this additional complexity that it varies periodically. It's density.
Yeah, but in the real world, there's no super solid proof yet. So how do you model?
Well, experimentalists are preparing these systems in laboratories. Like with,
they solid helium or which?
No,
system?
so it's like in a vacuum. Who was the lady who came and talked about astrochemistry and stuff like that? It's a similar setup like that, where it's like in a vacuum chamber. And they squirt some atoms in and they use lasers to sort of arrange them. Like she was even talking about like actual crystals. She was talking about them being like crystals.
Olivia Crow.
What?
Olivia.
Yeah.
Olivia.
Yeah. It's
I
similar
don't
to
remember
that.
she say anything about super solid.
Well, that's not what she's doing, but it's a similar setup to that.
Oh,
they
okay.
use.
That's why, how do you know your GRPA, what, random random phase
generalized-
approximation or
Yeah,
what?
generalized random phase
Oh,
approximation.
okay. So how do you know your generalized random phase approximation is correct? And you keep comparing your quantum Monte Carlo to something you don't even know whether it's correct.
Well, we're trying to assess that. That's what a big part of my thesis was. I mean,
Monte Carlo is not.
No,
to be
you are
exact
trying
for
to
this.
match in the quantum Monte Carlo with your GRPA. You basically assume that's correct, that's why you try to making the quantum Monte Carlo the same as your GRP.
no, it's the other way around. I assume that excuse me, I've already mixed up. I assume that QMC is correct, and then I'm trying to adjust GRPA by changing the potential energy factor that we use in GRPA. Because we have, it appears to be the case that QMC, at least for this system, gives exact results that are arbitrarily close to what the experimentalists tell us is true. At least for this system.
Yeah, hard for me to, without looking at the experimental data, I don't know what is this system is really based on, you know.
But you can mathematically prove that for this particular Hamiltonian, QMC is exact.
Oh, it's a mathematical proof?
It's a mathematical
Okay.
proof, yes.
Okay. Have they been able to prepare these?
Not really the super solid because
Okay.
it's too difficult to get the density exactly at half filling.
No.
They are trying to go there though. It's an ongoing effort.
Well, so, yeah, it sort of worked. That was the point. But it didn't really lead to any improvement for the, what we're really interested in, which is this SQ omega. So those are so that's what I call the physical potential. Here's what this optimized potential. Yeah, it's closer, but if anything, it looks worse actually.
I mean, it doesn't look terrible. I mean, you have like, on the bottom one, you have those two like small bumps,
Yeah.
but the gross overall feature seems to be okay. Where
Yeah, but this thing isn't, this thing is just a tool. It's not really something we're that interested in. It's a path to get to this guy. And it didn't seem like there was a huge advantage to this. It was just some idea we had and we wanted to try it out. It was really, the main affair is this stuff and this stuff. Yeah. So it sort of ends in a whimper, at least. So we calculated the dynamical correlation functions for a cold atomic gas in the supersolid regime. We used QMC to assess the quality of GRPA results. And we are starting to make calculations for a system in the dilute regime. So instead of having all these particles like packed together like this, like in a supersolid, there'd be a lot of more gaps, more empty lattice sites than particles, basically. And then there's always interest in sort of methodological improvements, like TD-DFT, time-dependent density functional theory. That's exciting and interesting and might be very powerful. I know there are people at Washington State who use that for these sorts of things. And then there's a sort of like really souped up version of GRPA and BCS called Hartree-Fock-Bogoliubov. And I didn't transliterate his name correctly, though I did in the other part. Should be a Y there. And then also I'm interested in just classical simple liquids with molecular dynamics, and that was more that velocity autocorrelation I was showing. And I'd like to maybe calculate these guys for that system as well, because you can do it and people have done it before, and it was more just interesting. So I just want to express my gratitude for my Indian tribe, the Chickasaw Nation. I feel like I should give a shout out to them because they basically funded my education because I'm broke, and then my family for encouraging me, and I want to thank Dr. Talley for guiding me through this research process and introducing me to all sorts of interesting topics, and Dr. Singleton and Dr. Munoz for your great classes and all that, and Dr. Ho and Dr. Kloster and Patrick Talbot, wherever the hell he is, for introducing me to chemistry and chemical physics, and yeah, and I want to extend my thanks to the Fresno State physics community for sort of opening the door for some guy who had some weirdo humanities degree. It wasn't very useful and wanted to remake himself. So yeah, thank you.
So thanks for a great talk. Not as many names as Joey's talk, but I wanted to say your humanities degree was not useless because I love reading your stuff. Like you write well, and so Gerardo's shaking his head, and so that's an important skill in science. Like you can do all the great calculations if you can't get it down on paper and convince other people, it's worthless. So I really enjoyed reading. So questions.
On slide 25, I think, you talked about how you, the
Oh, there's numbers there. I didn't even notice that. That's so convenient, thank you.
Oh, my bad, so it's 24 then. Yeah, so you talked about how you had, like QMC was the thing you know is true, and then you were changing a factor to try to get GRPA more accurate.
Yeah.
So, okay, so we have the F ones here, but I think on another slide you had S sub NN as well. Yeah, but is it these? Yeah, I think it's these.
Well, there's also where I actually.
Oh, here it is.
Is this what you mean?
Yeah, this is the one. Yeah, so which factor was the one that you were changing, or was it both of them that you were trying to adjust?
So, well, there was only one thing I was trying to change, and that was this the potential energy. That's the parameter that controls the strength of the potential energy in the BCS Hamiltonian.
Okay. So like, did both of these like have to do with that then, or was it?
So this one, I use the same strength. Well,
Okay.
I should say, we use the same strength in the GRPA that we used in our quantum Monte Carlo runs, which was -4. And then in this one, we used -4 for the quantum Monte Carlo. It's the same data, it's the same blue curve. And then we used the sort of optimized effective potential that we got through this sort of chi-squared procedure, where we tried to minimize this. See, there's a gap here. We basically found what is the U effective that minimizes this difference, that basically drags down this orange curve that you can barely see, so that it lies as close to, or it minimizes the disagreement between itself and the blue curve, using the chi-squared test.
And you were saying that like it didn't work out as well as you would have hoped, or?
It just didn't really, I don't know, it doesn't seem like it I don't know what we were really expecting, I don't know what I was expecting, but I guess I was expecting maybe that the GRPA data on this side would line up with the QMC data on this side better.
Okay, I'm with you.
Yeah.
Thank you.
Other questions? Yeah.
So will I guess this is for Joey too. Will the theses be available for students to read?
Well, if you're interested, ask them and they'll shoot you a PDF.
Yeah.
Yeah, I got mad copies if you want.
Okay.
And that reminds me, we're gonna buy you guys. We're buying a department copy, and then we're also buying you guys copies. So, and Dan, actually, that reminds me too. Do we buy you your copy?
I don't know.
Okay, well, that means we did. So,
Yeah,
so
because they have like a place in like the physics conference room, I think, where they have printed versions of all the old prior theses. So if they'll let you get to that, that's cool. But like, if not, I can also like just get your email contact info, and I can just like send you.
So then eventually, they'll get a copy, and then we have a departmental copy that kept in the conference room library. So you're welcome to come down, sit there, read, and let the knowledge flow over.
Don't they all go on to university microphones, don't they?
Yeah, so, I think you can download them from the Henry Madden library somewhere too. Yeah, I'm always suggestions on how that was featured. So, any other questions, comments?
Oh,
Go ahead, Joe.
yes. So you were talking about, so you did like the densely packed super solid or super fluid before, right? And then you were gonna like move on to like a more diluted setup.
Yeah,
So do you get like, do you still work with like the same like base Hamiltonians for that setup, or?
well, so what changes is which will change is the dispersion relation. So this guy here.
Okay. But
In this system, it's like a cosine function. In the dilute system, it's quadratic.
okay, but you still like look at like the same types of graphs, I guess, and it's like
Yeah.
they look different looking curves, or maybe what speed.
Yeah. For that, you get something that looks like
Yeah, like that. It goes up and then up.
yeah. It does. It looks like this. But imagine it can't change direction, go back down again.
Oh,
And then keeps going up. It doesn't go back down again to 0. But it has a kink like there and then keeps going.
What is your horizontal line meaning?
Momentum of the.
No, the dash line. You have two dash line in a
Yeah.
different place, what that mean?
That's the particle gap, like the energy it costs to like separate a pair, right? And the GRPA overestimates it.
You mean it's like a band structure, so that's another band, optical band on the top, something like that?
I'm not sure.
No, it's the gap. So it's how much does it cost to break a pair?
Oh.
It's
But
like the
why
BCS theory
quantum-
delta.
Why the quantum Monte Carlo, the gap is, there's a gapless part?
The quantum Monte Carlo is still the dash line. It's only lower than the other one because GRPA overestimates it quite a bit.
They are touching the curve.
Yeah, but that curve is the collective mode. So those are the sound waves. So you can excite those even without breaking the pair. So because you have the pair particle that oscillates like. So you have the fluid of pairs which does its own sound waves. While the horizontal line is if you just push that energy into the system, you break a pair. And the system gradually loses superfluidity.
But break the Cooper pair or?
Yeah.
So by messing with the effective potential, you guys were trying to do things like make the line come down closer?
Yeah, we try to like minimize the disagreement between the two approaches. But the problem is you fix a property and you damage another one. So
Yeah, you fix one problem and something else. Yeah.
So Cooper pairs are like, are essentially excitons, like phonons, or are they?
Well, I think they're quasi-particles, right?
Yeah, Cooper pairs are quasi-particles and phonons are quasi-particles.
I mean,
but
they're,
for this system here they are already in the ground state. You do not need to excite it to get Cooper pairs. Because since it's attractive, the particle combine in pairs. So your overall system is just a gas of pairs at the crudest approximation. Then QMC includes all the correlation effects. But on the left-hand side, you imagine that the system is just a gas of pairs, like a gas of molecules, and each molecule is a pair of two fermions, one spin up and one spin down. And they can be broad, they can be like...
But are they real physical things like gas molecules, or are they mathematical abstractions, like strings and string theory?
No, those would be real physical particles. And in particular, if you go to pretty strong attraction, those are very tightly bound that you really have like almost point molecules. if you have a pretty weak attraction, those are very delocalized. So you have a quantum bound state, but between two of them, you have a sea of other particles moving around. So it's a little bit less easy to visualize in a classical picture.
So they are real physical things, although they are not obligated to be easy for our human minds to understand.
Yeah, they are still quantum, so in that sense they meet.
Naturally.
There is no, I'm not aware of a classical counterpart of a Cooper pair. Although you can still imagine like two atoms combining in a molecule. Yeah, you can think of a molecule probably, that's the easiest one.
Okay. Further questions, comments? No? Well, if not, let's thank both speakers again.